This slide shows typical demand factors and diversity factors for power stations. In this column, you can see the type of consumer. This and this is a residence lighting. The type of consumer is lighting loads and residential lighting loads. So if residential lighting loads are less than their power is less than quarter of a kilowatt, then normally their demand factor is 1, which means that these loads, the lighting loads, normally in a residential area, nearly all the lights in a premises are switched on, which are connected are switched on. They may be switched on. So normally, typically, the demand factor of residential lighting load of less than quarter kilowatt is 1. So if you talk about lighting lights whose rating are, let's say, 500 kilowatt 500 watts. So for such lights whose rating is 500 watts, the demand factor is 0.6, which means that the connected lights may be more than the lights which are actually switched on. And over 1 kilowatt, which is which falls under the category of commercial lighting as well. So over 1 kilowatt, if there is a light of over 1 kilowatt, then its demand factor would be typical demand factor would be 0.5. Similarly, you can interpret the different other demand factors as well. And in the bottom table, you can see the diversity factors, typical diversity factors. So for residential lighting, for commercial lighting, and for general power supply, different diversity factors have been described in this table, and you can use these diversity factors in the problems as well. If the data is not given and these tables are given, you can use diversity factor from these tables. Now we move on to load duration curve. So load duration curve is obtained by arranging load elements of a load curve in descending order of magnitudes. I am going to throw light on it in a bit. So gives data in more presentable form, as it readily shows the number of hours for which a given load has prevailed. So let's say this is the load curve, which is showing you at what time what load was present on the power station. So typically we are more concerned with with the fact that for how many hours was a particular load present on the power system. So let's say if we talk about 20 megawatts. So 20 megawatt load was only occurring in the power station for from 8 to 16, from 8 a.m. to 4 p.m. So from 8 to 4 it is 8 hours. So for 8 hours 20 megawatt load was present in the power station. So first of all, in a load duration curve, you plot 20 megawatt from 0 to 8 hours, which shows that for 8 hours 20 megawatt load was in the power station. Then 15 megawatt, if you say how much for how much time 15 megawatt or less load was in the power station. So you can say that the load was 15 megawatt for from 4 a.m. to 16 or 4 p.m. From 4 a.m. to 4 p.m. the load on the power station was 15 megawatt or greater than that. So you can plot it like this. So the 15 megawatt load, or if you look at even if you simplify this explanation, that 15 megawatt load was occurring in the power station for only 4 hours, from 4 a.m. to 8 a.m. So if you plot this from 8 to 12, you can say that the 15 megawatt load was in power system for 4 hours from 8 to 12. Secondly, you can also tell that the load was greater than 15 megawatt for a total of 12 hours. Was 15 megawatt or was greater than 15 megawatts for a total of 12 hours. Then if you talk about 5 megawatts, then you can see that 5 megawatts load is from 12 a.m. to 4 a.m., which is 4 hours, and then from 4 p.m. to 12 p.m. 4 p.m. to 12 a.m. So that is a total of 8 hours. So for a total of 12 hours, 5 megawatt load was present in the power system. From 12 to 24, you can see that the difference in the hours is 12. So for 12 hours, 5 megawatt load was in the power station. Or you can say that for 24 hours, the load on the power station was equal to or greater than 5 megawatt. So based on this curve, based on this load duration curve, uh, you can uh, present a generation schedule for different power stations. For example, you may say that for 24 hours, our thermal power plants, coal power plants of 5 megawatt, our coal-fired power plants will generate 5 megawatts for 24 hours straight. Why are you not opting to turn off the thermal power plants? Because their startup time, as I have told you in the steam power in the previous lectures, that the startup time of coal fired power plants is around 8 hours. So once you shut them down, you cannot harness electricity from them for another 8 hours, and that startup process also takes up a lot of money and a lot of energy. So that's a waste of energy. So in general, we like to keep our coal-fired power plants in operation unless they have to be shut down for maintenance. So you will say that for to serve this 5 megawatt for 24 hours, you will uh, run the thermal power plants for 24 hours. Then you can say for this extra 10 megawatt during the 12 hours, you can run a hydroelectric power plant for that time of 10 megawatt. And then you can say for you can run a nuclear power plant of 5 megawatt for these 8 hours. So this is how generation schedules are made using load duration curves. So what will happen now is that if you look at the load curve, then the steam power plant will be operational for all of the time. The hydroelectric power plant will start operation from 4 a.m. and it will continue operation up to 4 p.m. while the nuclear power station will come online from 8 a.m. up to 4 p.m. and supply the extra power. And all of that is derived from this load duration curve. Let us look at some examples. So maximum demand on a power station is 100 megawatts. If the annual load factor is 40%, compute the total energy generated in 1 year. So if number of hours, this is exactly what I was talking about previously, that if you are given the number of hours in a year for which the plant is operational, then you will use those number of hours. But if also you have to consider if you are required to compute plant capacity factor or plant use factor. So that is a distinction you need to make. But other than that, for all the other problems, to compute the average load, let's say, you have to consider the number of hours the plant was in operation. If these hours are not mentioned in the example, then you can take them as 8760, which are the total number of hours in a year. So for this problem, we can take 8760 hours. So first of all, you are given the load factor, you are given the maximum demand on the station. You know that the formula for load factor is average load divided by maximum demand. So you can find out average load from this formula. Multiply load factor with maximum demand, you get 40 megawatts, and the total energy generated in a year will be 40 megawatts, which is equivalent to 40 into 10 to the power 3 kilowatts into 8760, which is the number of hours, and this energy will come out in kilowatt hours. So you get 350.4 into 10 to the power 6 kilowatt hours of energy, or you can say 350.4 into 10 to the power 6 units of energy, or you can say that the energy generated was 350.4 gigawatt hours. Remember that normally a unit of electricity is taken in kilowatt hours. So if you are representing energy in gigawatt hours, you cannot say that you are generating 350.4 units of energy. You are actually producing 350.4 into 10 to the power 6 units of energy, which you can choose to represent in gigawatt hours as 350.4 gigawatt hours. So take care of that. In this example, we have a generating station which has a connected load of 43 megawatt and maximum demand of 20 megawatt. The units generated being 61.5 into 10 to the power 6 per annum. So 61.5 into 10 to the power 6 kilowatt hours per generated per annum. Compute the demand factor and the load factor. Demand factor is given by the following formula, which is maximum demand divided by connected load. So maximum demand and connected load is given to you. You can easily find out demand factor. Average load is given by the units generated per annum divided by the number of hours in a year. Again, though the number of operational hours are not given to you, so average load in this case will be taken as a ratio of units generated per annum divided by 8760. If in papers I give you that the plant was in operation for 5000 hours in a year, then you cannot compute average load by units generated by annum divided by 8760. You have to put units generated per annum divided by 5000. In that case, you can clarify this if you want in the QA sessions. So the energy which comes out for our example is not energy, power which comes out, average load comes out to be 7020.55 kilowatts. So load factor is given by the formula average load divided by maximum demand. So if you do that, you get this load factor of 35.1. In this example, we have a 100 megawatt power station that delivers 100 megawatts for 2 hours, 50 megawatts for 6 hours, and is shut down for the rest of each day. It is also shut down for maintenance for 45 days in each year. Compute its annual load factor. So you have to consider all of this schedule which has been given to you in calculation of average load. So total days per annum for which the plant is operation is 365 days in a year minus 45 days for which it is shut down. So total days for in a year for which the plant is in operation is 320 days. So total hours per annum for which the plant gives 100 megawatts. So 100 megawatts power is only delivered for 2 hours in each day. So if there are 320 days, then the number of hours for which 100 megawatt power is given, then those total hours are 640. And total hours per annum for which plant gives 50 megawatt is 320 multiplied by 6, where 6 is the number of hours for which 50 megawatt is delivered. So you have to find out total energy generated by using these two informations. So total energy generated per annum is 100 megawatts for 640 hours. So 100 into 10 to the power 3 kilowatts for 640 hours plus 50 megawatts or 15 to 10 to the power 3 kilowatts for 1920 hours. That will give you energy in kilowatt hours, 160 into 10 to the power 6 kilowatt hours. Maximum energy that can be generated per day can be found from this. It's not per day, actually it's yearly, but it's per year, per annum होना चाहिए. So it's not per day, it's per annum. This is a typo. So 100 into 10 to the power 3 is the maximum demand, maximum energy that can be generated. So 100 into 10 to the power 3 into 320 days into 24 hours per day. So you get 768 into 10 to the power 6 kilowatt hours. So annual load factor is the ratio of these two. So that comes out to be 20.8%. In this example, we have a generating station that has a maximum demand of 25 megawatt, a load factor of 60%, a plant capacity factor of 50%, and plant use factor of 72%. You have to find out reserve capacity of plant, daily energy produced, and you have to find out maximum energy that could be produced daily if the plant, while running as per schedule, were fully loaded. So it is running as per schedule given to you, and it is fully loaded to its capacity. So reserve capacity is equal to plant capacity minus maximum demand. So we know that average load is equal to load factor into maximum demand, that is 0.6 into 25 megawatt, which will give you 15 megawatt. So plant capacity will be, as we have derived this formula, plant capacity is equal to average load divided by plant capacity factor, or plant capacity factor in effect is equal to average load divided by plant capacity. So you can find out from this average load and plant capacity factor which is given to you, you can find out plant capacity that comes out to be 30 megawatt. So reserve capacity can be easily calculated now, 30 megawatts minus the maximum demand which is 25 megawatt. So 5 megawatt is the reserve capacity. Daily energy which can be produced is average load on the station multiplied by 24 hours of the day, that is 15,000 kilowatt, because 15 megawatt, that is the average load. So 15,000 kilowatt into 24 hours, so 15,000 into 24 kilowatt hours, 360 into 10 to the power 3 kilowatt hours. So maximum energy that could be produced daily is this 360 into 10 to the power 3 kilowatt hours divided by the plant use factor, for which the plant use factor, remember that it is showing you for which the plant is actually in operation. The maximum actual energy which was produced divided by the maximum energy that was produced, that could have been produced if the plant was in operation given the schedule. So as per schedule, the thing is asking you to do it as per schedule, which means you have to use plant use factor. Plant use factor is utilized here, and you find out that maximum energy that could have been produced if the plant was running as per schedule, which determined the appropriate plant use factor, that comes out to be 500 megawatt hour. In this example, we have a diesel station which supplies the following load to the various consumers. So for industrial consumer, this diesel station supplies 1500 kilowatts. Commercial establishment gets 750 kilowatts from it. Domestic power gets 100 kilowatt. Domestic lights get 450 kilowatts. If the maximum demand on the station is 2500 kilowatt and the number of kilowatt hours generated per year is 4500 times power 5, determine the diversity factor and the annual load factor. Diversity factor is easy to do because these are all maximum demands. So these maximum demands can be summed up and divided by the maximum demand that occur on the station. That will give you the diversity factor of the plant as 1.12. The average demand on now you have to find out the load factor. For that you need average load or average demand. So average demand is the kilowatt hours generated per year divided by the hours in a year. So 445 times power 5 divided by 8760 gives you 513.7 kilowatts. So load factor can be easily found from the average load divided by maximum demand. Maximum demand is given to you 2500 kilowatts. Average load is from here. So the load factor of this power station is 20.5%. A power station has a maximum demand of 15,000 kilowatt. The annual load factor is 50% and plant capacity factor is 40%. Compute the reserve capacity of the plant. So first of all, for any given problem, if you are given the load factor and maximum demand, you can easily calculate the average load. You have to find out the reserve capacity of the plant, which is very simply calculated by plant capacity minus the maximum demand. So maximum demand is given to you. You have to find out the plant capacity. So the annual load factor is given to you. Maximum demand is given to you. You can find out the average load. Once you have this average load, you can use this formula of plant capacity factor is equal to average load divided by plant capacity, or plant capacity is equal to average load divided by plant capacity factor. That will give you 18750 kilowatt. Reserve capacity is obviously this capacity minus maximum demand. So reserve capacity of the plant is 3750.